Hi everyone. What we're going to be learning about today is how we can classify or categorize a chemical equation into one of 5 main categories. So what you need to have out are your types of chemical equations notes that you printed, or if you don't have printing capability, then you need to have out notebook paper and take really good notes for yourself. Okay? So we can categorize chemical equations lots of different ways, but the way we're going to be doing it is by a particular type. So our first type of chemical equation that you see here is combustion. All right, so let's read what combustion is first off. Combustion is when we have the burning of a hydrocarbon in the presence of oxygen to form carbon dioxide, water, and energy. All right, now let's pull that whole statement apart. There's a lot of information in that statement. Okay, first off, combustion means something is burning. It means something is on fire. Okay, that's what combustion means. So if we say that your piece of paper is undergoing combustion, it means your paper's on fire. If we said that your Bunsen burner is on fire, it means the methane is on fire. Okay, what that means is something's burning, and the substance burning is what we call a hydrocarbon. A hydrocarbon is any compound with carbon and hydrogen in it. It might have any number of carbon and hydrogen atoms in it. So we use X's just to represent any numbers of C's and H's. So the first thing that you're going to do when you want to try to find a combustion equation is you look for a hydrocarbon. Look for a compound with carbon and hydrogen on the reactant side. And it has to react with oxygen. Okay? In the presence of means that the hydrocarbon has to react with. And that means it has to react with oxygen. All right? And oxygen is written as O2. So to identify combustion, you're going to look for something that has in it a hydrocarbon as a reactant and oxygen as a reactant. So if you look at these two examples, we can see that we have a hydrocarbon here, something made of C and H, and a hydrocarbon here, another molecule made of C and H. And in each instance, those hydrocarbons, and again, they're called hydrocarbons because they are made of carbon and hydrogen. Yes, the carbon is first. So you would think it would start, the name of the compound would start with carbon, but it doesn't. It's a hydrocarbon. So in both of these examples, you see the hydrocarbon and it's reacting with the oxygen because fire needs oxygen to burn. Without oxygen, fire will burn out. So a hydrocarbon has to react with oxygen. And we see oxygen in both of those. Now, the interesting thing is anytime this hydrocarbon reacts with oxygen during combustion, the same compounds are made every time. Carbon dioxide, which we know as CO2, water, which we know as H2O, and we know that when something burns, there's heat and light made. You see light and you feel heat when you have a fire. That's the energy here. All right. So the way that you look for combustion is, again, you have to have the hydrocarbon reacting with oxygen, but on the product side, you also have to have very specific compounds. You have to have carbon dioxide, which both of these examples does. You have to have water. So, yep, fire makes water. Not a lot of it, but it does make water. And you need energy. That's the heat and the light. So remember, the energy that we see here, that's the heat and the light that we get from fire. And every combustion reaction is going to look like that. So let's look at another example. So let's write this example on our paper. Let's say that we are burning octane. Okay? In this first example here, the CH4 is methane. That's what happens when we light a Bunsen burner on fire. That's the reaction that happens when we burn methane. This C4H10 in the second example, that's butane. That's lighter fluid. If you've ever used a lighter, that's butane that's burning. Well, octane is gasoline. Next time you're at the gas pump putting gas in your car, look at the fuel pump. It even tells you it's octane. Octane is C8H18, and that's what your car does when you put gas in it. It takes this octane and it reacts with oxygen in the air to burn it. And coming out of the exhaust in your car is carbon dioxide and water and heat. Now, in this combustion, we don't have light. You know, when you're burning gasoline in your car, you don't see light, but you do have heat, okay? If you think about the hood of your car as your engine is working, it feels hot because that's the heat that's being released as a part of the burning of the octane. Okay, if we look at another example, let's say this time we're burning propane. What's in a gas grill? Well, propane is C3H8. And anytime you light that gas grill on fire, anytime you light this propane hydrocarbon on fire, again, it's reacting with oxygen, and it's going to make carbon dioxide and water and energy. So notice that in each of these combustion equations, after the hydrocarbon, everything is identical. You're always going to have the plus O2 make CO2, water, and energy. Okay? Now, the CO2, the water, the energy can be in any order. I could write water and then the CO2 and then the energy. Or I could put the energy and then the water and then the CO2. The point is, are they products? Are they always to the right of the arrow? Okay? So in a combustion equation, you're simply going to be looking for a hydrocarbon. Let's try that again. You're going to be looking for a hydrocarbon reacting with oxygen, and every time you're looking for it to make CO2, water, and energy. Don't rely on energy to identify combustion because sometimes energy won't be shown to you. So for example, if I were to remove energy from this equation, it's still combustion. Energy is sometimes not shown because energy is not matter. And chemical equations typically show the rearranging of atoms or matter. Okay? So that's our first type of equation. The burning, the combustion of a hydrocarbon. All right? Now, our second type of equation is known as synthesis. Now, the word synthesis means to make. That's what synthesize means. So if you are synthesizing something, you are making something. Well, every chemical reaction makes something. That's what makes it a chemical reaction. You make new things. What makes synthesis reactions unique is you make one compound on the product side. So if we look at this first example, here is our arrow, this is our product side, and you see one compound. That's a compound because there's two capital letters. Okay, remember two capital letters stuck together like that's a compound. So if you notice, there's not a plus anything else over here. All we see on that product side is compound AB. We don't have plus anything else. Okay, now if we look at the second example, again, here is our arrow, and this is our product side, and we have one product. Yes, I know that you see a 2 there, but there's only one compound on that side, H2O. So that's one product. We are synthesizing, we are making one product. So if you have one product, there's not plus anything else to the right of the arrow, then it is a synthesis reaction. All right, so again, you may want to make this as a note. Synthesis will have one substance to the right of the arrow. Okay, one substance means one compound. We're not looking at this coefficient 2 here. That has nothing to do with the compound. The compound is water. We have one compound over there, water. Okay, so notice here we had 2 reactants, we made one compound. 2 reactants, we made one compound. That is synthesis. Okay, the third type of chemical equation is what we call decomposition. Now think back to biology. What do decomposers in a food chain do? Right, decomposers break down dead and dying and organic matter. That's what decomposition in chemistry means. It means to break apart. Okay, decompose means to break apart. And you're not just breaking apart anything, you're breaking apart one compound on the reactant side. So you're breaking apart one compound on the reactant side. That means you have one substance to the left of the arrow. So if we look at our arrow here, to the left, we have our reactants, and there is one substance on that side, compound AB. That is why this is decomposition, because it broke it apart into what it was made of, element A and B. Okay, if we look at this next example, we have one reactant here, the CaCO3, notice. So this CaCO3, this is on our reactant side. There's one reactant. Okay, it broke apart into what made it, which was the CaO and the CO2. Okay, so again, decomposition means to break apart. You're taking one substance and you're breaking it apart into what made it. Okay, so you can think of decomposition almost like an egg that is hatching. So if I had an egg here and it hatched, well, I'd have a broken eggshell, right? And out of it, I might hatch a little baby bird, right? I can't draw, so I'm not going to even attempt to draw a little baby bird for you. But that's decomposition, okay? Why would that be decomposition? Because I start with one substance on the reactant side, okay, which is my egg, and it breaks apart in over here to a broken egg and then a baby bird. So I took one thing, broke it apart into two or more. That's decomposition. All right. So let's take a look at another example. Single displacement or replacement. It can be called single displacement. It can be called single replacement. Same thing, no matter which term is used. I will call it displacement. Single means one, right? It means one element is going to replace another. One element's going to switch places with another. So it'll always have this general form. You'll always start with a single element. How do you know if you have a single element? You have one capital letter. So A represents a single element. It's one capital letter. And that single element will always react with a compound. Okay, so here we have a compound, two capital letters. And in this reaction, one element is going to switch places with another. One element is going to kick out another one. So if we notice in this example, A kicks out B. How do we know that? Because B is alone over here. And now A and C are together on the product side. So it's almost like A was one person all by himself, and B and C were a couple dancing, and A came over and said, "Can I cut in?" And you made a new couple over here. So how do we know if it's single? You look on the reactant side, you look for an element and a compound, then you look on the product side. You should make another new element and a new compound. Here we have a new element, B, and a new compound, AC. Okay? Double displacement, double refers to two. It means two elements are switching places with each other. If two elements are switching places, it means we have to start with compounds everywhere. My reactants both have to be compounds, and my products both have to be compounds. That's the only way that two elements can switch places. So if we notice in this example at the beginning, two elements did switch places. A came and switched places with C so that A and D could form a new compound, which meant B and C were going to form a new compound. And that's what you see over here. We have CB. Okay? So that is how you're going to be looking for the different types of equations. Okay? You're either going to have combustion, where something's burning, a hydrocarbon's burning in the presence of oxygen, making CO2 and water. Or you're going to have synthesis, where you make one product. Or you're going to have decomp, where you take one reactant and break it apart. Or you'll have single displacement, where there's an element and a compound on either side of this arrow. Or in the fifth and final type, we'll have compounds everywhere. Both compounds on the reactant side, both compounds on the product side. Okay, those are your 5 main types of equations. So what I'm going to do now is I'm going to do some practice with you. So I am going to do the practice with you. That's number 1 through 5 in your notes. And then you will do 6 through 13 on your own. Okay? But after you have labeled 6 through 13 on your paper, you're going to want to come back to the Zoom so that we can enter questions 6 through 13 into a Desmos that I'll have. okay? But I won't put the Desmos up to put those answers in until everybody has finished going through the video and practice problems 1 through 5. Okay, so let's look at 1 through 5 together. All right, so what type of equation do we have here in number 1? Okay, remember the 5 types are synthesis, decomp, combustion, single displacement, and double displacement. So if you're not sure, you can always use a process of elimination to kind of figure it out, right? So if we look at these 5 types in comparison to number 1, would number 1 be decomposition? No, because decomp has 1 reactant, and notice over here on the reactant side, we have 2 things. So it can't be decomp, so we've eliminated decomp. All right, now, is it combustion? We see oxygen. Is that combustion? No, it's not combustion because the other reactant's not a hydrocarbon, doesn't have carbon and hydrogen, and the products are not CO2, water, and energy. So we've eliminated decomp, we've eliminated combustion. What else do you think it might be? All right, so for this one, what we notice here, our key characteristic is that we have 1 product. So notice over here on the product side, there's 1 product. That 2 has nothing to do with anything, okay? You have 1 compound over here on the product side. 1 compound, we made 1 thing. That is synthesis. Synthesis is unique because it's only going to make 1 compound. Most every other chemical reaction, well, all other chemical reactions, in fact, make more than 1 compound on the product side. There would be a plus and something else written over here, and there's not. That is what makes synthesis unique, is because there's only 1 product. There's not plus anything else. All right, what type do you think number 2 is? Okay, so if we notice here, we have an element because it's a single letter, a single capital letter. This reactant is a compound. This product is an element. Yes, there's 2 letters, but only 1's capitalized, so that's an element. Here we have 2 capital letters, that's a compound. So which one takes the general form element plus compound makes element plus compound? Good, that's single displacement because 1 element took the place of another. Okay, in this example, potassium kicked out magnesium. Potassium and chlorine bonded to make a new compound, and magnesium was left all by itself. We had 1 thing switch places. Okay, in number 3, what type of equation do we think we have? Okay, we don't have combustion. Okay, first off, oxygen here, that oxygen that we just highlighted there, that's not a reactant. Okay, we don't have a reactant that's a hydrocarbon, and we don't have this water here as a product. So remember that for something to be classified as combustion, it has to look just like this. You have to have some type of hydrocarbon reacting with oxygen, making CO2, water, and energy. Sometimes the energy will be shown, sometimes it won't. So that's why that one is not combustion. Okay, so what is it? Good, it is decomposition. Why is it decomposition? Because we have 1 reactant. We have 1 compound on the reactant side. It's breaking apart into what made it. So this shows the decomposition of water. This is H2O, and it's breaking apart into what made it, hydrogen and oxygen. All right, number 4. What type do we see in number 4? Okay, good. This is double displacement. This is double because we have a reactant here that's a compound. We have a reactant here that's a compound, and it's made a compound and a compound. These are all compounds because they all have more than 1 capital letter in them, right? Which means we had 2 things switch places. The lead switched places with the potassium so it could attach to the iodine. See over here we have the PB and the I together, which meant that the NO3 and the K could be together on the other side. So 2 elements actually switch places, hence double. Double is 2. Okay. Let's take a look at number 5, the last one I'll do with you. All right, what type do we think number 5 is? Okay, it can't be double. It can't be double displacement because oxygen is not a compound. We don't have compounds everywhere. Yes, this C and H, that's a compound. The CO2 is a compound. The water is a compound, but the oxygen isn't. So it can't be double displacement. It's only double if everything is a compound. 2 compounds on the reactant side, 2 on the product side. All right. So what else might it be? Okay, it can't be single because we don't have an element on the product side. For it to be single, you have to have one element on either side of the arrow, and we don't. So what does that leave? All right, well, let's look at it. This thing with the C's and H's, that's a hydrocarbon. It's reacting here with O2, oxygen, and it's making carbon dioxide and water. That is combustion. Very good. That means this is on fire. That CH18, the octane, the gasoline's on fire. Okay, that's what's happening in the internal combustion engine of your car. Notice we didn't show the energy over here. Notice there's no plus E. That doesn't mean it's not combustion. It just means that we're choosing not to show the energy. Energy is not matter, and chemical reactions typically focus on showing you matter. Okay? All right, so we've practiced the 5 types of equations together. So now you are going to do 6 through, let's see how many I asked you to do, 6 through 13 on your own. So notice you're going to do 6 through 13 that are left on your own. And I will call you back together in the Zoom, and we will put those answers into Desmos so that I can check your accuracy on that. All right, if you have any questions, send me a chat, and I will be happy to answer it.